4.6 is on what's called variation of parameters, and this method is a little more general method to solve a linear non-homogeneous case. So we're basically going to derive the method, the formula, and see how it works. So let's first consider the standard form of that equation. So consider the equation. We'll call this equation 1. A double prime. So this is just the same as we've had before. A double prime plus B prime plus CY equal to some function. We'll say some function of T. So specifically, it's non-homogeneous. And second order linear. So the development goes like this. We're first going to let y1 of t and y2 of t be two linearly independent solutions to the homogeneous case. So this is typical, is what we've done before. And they're linearly independent, so when you get that Wronskian in that denominator, it's non-zero. That'll come later. When you solve, you'll see how it goes. Okay, so their solutions to A double prime, BY prime, plus CY equal to 0. Okay, then we know that the homogeneous solution is the sum of those two with constants. YH homogeneous of t equal to C1 Y1 of t plus C2. Messed that up. Print the C up there, didn't I? Y2 of t. Okay, so that form, as we know, is a general solution to this case here. And then C1 and C2 are constants. So this is all kind of typical stuff. C1, C2 are reals or constants. So to find a particular solution, we look for this form. So we're basically going to work backwards. So to find a particular solution, we seek to find a solution in the form probably come back down here. So y particular of t is going to be this form. So it's v1 of t, so we're going to say some function of t, and then your y1 t plus v2 of t, y2 of t. So it's almost like for the particular, we're going to assume those are the A and B in front of the homogeneous, or C1, C2 in front of the homogeneous are going to be some functions of t, and we essentially are going to solve for V1 and V2. Doing so, we have to use some of the methods we have used in the past and solve it. So just write that up. So we will use, I can write that decently again. We will use similar methods solving the first order equations. This will be in second order, of course. Okay, so we do that to find V1, V2. All right, so what we want to do then is substitute. So we want to substitute all of this. So substitute this guy into 1, into equation 1. So by doing so, we need to expand it out. Meaning, well, not expand it out. We need to do this first and second derivative of this. All right, so first calculate y particular prime and double prime. So y prime then is, you need to use the chain rule, so you get product rule, product rule on that. You get v1 prime y1 plus v2 prime y2 plus v1 y1 prime plus v2 y2 prime. Now, this is where it gets a little strange. For y double prime, we don't want to have too many second derivatives. Because if you did the second derivative case, you're going to have all those with a bunch of second derivatives in there. So basically, without losing too much information, we can make a restriction on one of those. So I'll write up what I mean. So basically, we're trying to solve for v1, v2 by doing this method. And if we restrict it and it doesn't hurt what we're trying to look for, then we can do that. It's almost like it's almost like an overdetermined equation. You don't need so many variables to solve a system. That kind of idea. So for y double prime, and let me write that up. We do not want too many second derivatives. So we're going to impose this restriction. We're going to assume or impose that y prime, y1 prime, so I keep saying y, v1 prime y1 plus v2 prime y2 is equal to 0. So, where is it? This one. We're going to assume this is equal to 0. In doing so, it doesn't, like I said, the only way I can really help you here is that it doesn't hurt our solution. We have enough information to continue to solve. Right, so I did say that as well. Since the book doesn't really explain it easily, they just say, yeah, this works. But that's basically the concept. Since there is enough information or known quantities to solve for V1 and V2. All right, so doing so, we get this. Thus, y1 prime is equal to v1 y1 prime plus v2 y2 prime. And so when we take the second derivative, y double prime it's not as messy, basically. You get v1 y1 prime, oops, prime prime, plus v1 y1 double prime, plus v2 prime y2 prime, plus v2 y2 double prime. Now substitute into the first equation. So f is equal to a y particular double prime plus b y particular prime plus c y particular. So that's what we're going to substitute into and expand it and simplify. So we get a times the quantity, and then it is the y prime, so it's all of this oops, copied the wrong one. It's the double prime, so it's all of this. This gets substituted into here. Okay, so then it's plus b, so then this will be next. Then it's plus b times all of that. And then plus c times what was assumed, so that was v1 y1 plus v2 y2. So we distribute and combine. I went ahead and showed that step, I think. So you get a v1 prime y1 prime plus a v1 y1 double prime plus a v2 prime y2 prime plus a v2 y2 double prime plus b v1 y1 prime plus b v2 y2 prime plus c v1 y1 plus c v2 y2. Now we want to factor out and rearrange terms. So we look for let's see. Where did it go? So here's your A. So A v1 y1, A v2 y2. So here's v1 y1, v2 y2. And then we also have, let's see, where did it go? Yeah, so I'll just have to write down what it is because it's hard to show everything. So you get A and then v1 prime y1 prime plus v2 prime y2 prime. Those are the first two I highlighted. Then v1, so v1 is what you're factoring out next. So here's your v1, here's your v1, and your v1. By doing so, you get a y1 double prime plus b y1 prime plus c y1 plus, do the same thing for v2. Then you get a y2 double prime plus b y2 prime plus c y2. And so you're rearranging and forcing into a form that we can show or see that this is 0 and so is this. All right, so both of those end up being 0. Right, because because y1 and y2 are solutions to the homogeneous case, so that has to equal 0. So that's equal to all of that. So a v1 prime y1 prime plus v2 prime y2 prime, and then plus 0, I'll just say plus 0, since y1 and y2 are solutions to the homogeneous case. So now you have f equal to that. Okay, so then we have that f over a is equal to v1 prime y1 prime plus v2 prime y2 prime. So we have this system then given that equation, and we need another equation. So the other equation we already assumed is 0. So back here, so basically what we can do now is solve this equation and this equation as a system. So you get y1 v1 prime plus y2 v2 prime equal to 0, and y1 prime v1 prime plus y2 prime v2 prime equal to f over a. So this is a 2 by 2 system, and that's what you'll basically end up doing when you solve. Okay, you'll solve this system. So this is a 2 by 2 system, linear, so it can be solved by Cramer's rule. So, excuse me, what you'll get, v1 prime, when you solve this by Cramer's rule, you'll get this. Now, this is basically where I want you to stop. Okay, so right here, basically, solve system, then integrate for v1 prime, v2 prime. When we do it examples, it'll make more sense. Basically, you just have to set that up and it'll just integrate, but I wanted to show you at least a semblance of derivation here. So you get y1 2 prime minus y1 prime y2 and let me move that over here somewhere. Let's shrink that and just move that over here. Okay, let's see. So then you get v2 prime when you solve that. It's just the negative of it. F y1 a, and then y1 y2 prime minus y1 prime y2. And the denominator there is the Wronskian that's non-zero. So let's just point that out. So that's the Wronskian. So we know the solution exists because that's not assumed to be linearly independent. So by lemma 1, that Wronskian equal to y1 y2 prime minus y1 prime y2 is non-zero, since y1 and y2 are linearly independent. So then you basically just integrate that and you have your solution. So v1 of t is the integral of all of that. Let's just push that over there. dt. And similarly, v2 of t is equal to that integral of all of this dt. So I think we've done enough for this video. I'll do a summary of results and method of variation parameters, and then we'll go into doing examples, which should probably be okay. I'll probably just copy it over. That'll work. Okay, so this method is a derivation to kind of more generally solve and not have to guess what to do. And it'll look familiar of what we're solving, basically, of all this. So kind of bear with me here. When we look at examples, I think it'll make a lot more sense. We do not want to jump straight to here, okay? We want to basically get to here, excuse me, and then we can solve the system as you normally would. Eliminate a parameter, and then solve it, and then integrate. So we'll see that next.